All right, you made it to the final review. I can't go over everything, but I'm going to do my best to give you the most bang for your buck. Hopefully, what you see from these slides will help you figure out what you need to study harder. All right, so that's the goal at least. So yeah, let's get on into it. The first thing I've done is made a beautiful cheat sheet for you. If you want to use any piece of this, of course, you'll have to handwrite it on your actual cheat sheet for the test, but here's some stuff, nice color-coded stuff about pointers, recursion, exceptions, bitwise stuff, and makefiles. So you're welcome. I worked very hard on this, and yeah, we'll come to that eventually. But before we get there, I want to talk about older stuff that I covered in previous tests that you're never allowed to forget, all right? Stuff that is just going to be important for the rest of your computer science career, so we better go over it once more, all right? So let's talk about references. I know I've already tested you on this, but we better go over it again, all right? So a reference is just another name for an existing variable. It's an alias, a code name, secret agent. So you know how to make normal variables. Int x equals 42. That makes a box called x holding 42. And then you can come along and say, I want to give a second name to that box. You can make a reference to x. Int reference, let's call it y. Let's let that be a reference to x. And what that does is it doesn't rename the box, it gives it a second name. All right, it's a code name, it's an alias. Usually, and now you can say x or y, and it would affect this box and this value. So that's kind of cool. Usually you don't make a reference variable inside of a function. Usually you use references with parameters. You make reference parameters because that lets you pass your own memory to somebody else, which is nice, so that they can touch it potentially, and then also to get some space savings. You don't copy any values when you're just passing references because you're talking about the same place in memory. That's super nice. So don't forget about const references as well. Those are very important, right? Because sometimes you want to have this idea. You want to not be able to copy stuff and get the space savings, but at the same time you don't want to be able to accidentally touch that memory that was given to you. All right, so const references solve that problem. And yeah, let's just have some examples of references. Let's do a swap example. So we'll have a function that takes two things and it's supposed to swap those things. All right, so remember that there's a couple ways that we can make this function. You can do call by value where you make copies and that won't actually do anything. Remember that. I'll show you that example again. And then call by reference is if you use reference parameters, they're actually going to let you do it, let you touch the original memory. All right, so yeah, let's go talking about that. And I think that's a good place to start. Of course, you can also do pointers now. Do call by address. We'll get there. Okay, let's make a new file. I'll call it references.cpp. And so yeah, my first example, let's do a swap function. So let's have some variables, int I don't know, a equals 42, int b equals 43 in main. And then let's have some swapping functions. Let's have a swap by value function that takes a and b. And this one is not going to work right. It's just going to copy things, so it's going to be passed by value, which is unfortunate. So that's the original problem, right? Swap by value. Let's call these two things x and y. So it will swap x and y, but those won't be a and b. So here, let's do it's int temp, right, equals x, x equals y, y equals temp. That'll swap x and y, but those weren't the same places in memory as a and b. So let's see that not working. So this will fail. All right. So there we go. It's still 42, 43. Nothing happened. Remember that in the interfunction dreamland, x got set to a and y got set to b, but those are brand new places. These are just for the stack frame for swap by value. And so it swapped this x and y. These are separate places than a and b, though. So no real effect happened there. All right, so that's that one. And you know that you can solve this problem by using references. We'll do call by reference. That lets you just give another name to somebody else's memory. So what do I want to call this? I'll call it swap by reference. And you just got to add an ampersand here, and it solves everything. So here, let's change this to a call to swap by reference, and this one will work. Bam, I do get the first time it doesn't work, but then I get my 43, 42. Gotta run again. There we go. See there? Nice. So yeah, what's happening is this int reference x is being set up and being equal to a, and int reference y is going to be set up and equal to b, And those are just other names for A and B. So when I say X and Y up here, I'm really touching A and B down here. I get the effect that I wanted. All right, so that's called by reference. That's lovely. And that's one thing that references are good for. You want to touch somebody else's memory and mess with it. So another good reason to use references is if you don't want to copy stuff, right? Or maybe both at the same time. So let's pass a giant vector to a function. Let's say it's like size 1,000, but you can imagine it could be size 1,000,000. Like, let's fill up a vector with like a bunch of 42s. 42, 42, 42. Let's do like 1,000 42s. But you can imagine, pretend that it's size 1 billion or something huge, because if you called your function by value, it would be copying that vector, making another billion things. That's no fun. That might run out of memory. So we can solve that though. So let's pass the original vector by reference. So I better make a vector now. Let's make a vector int v, and let's use the fill constructor to make 1,000 42s all at once. That's beautiful. So now v is a vector holding 1,000 elements, each set to 42. There. All right, and then yeah, what we want to do is make like a summing function. So sum on v takes the vector by reference so that it doesn't copy it, it just uses the values. So we should take it by constant reference, shouldn't we? So int sum, not just a normal vector int v. We'll take it by reference so that we get our space savings. We don't have to copy it. And then we'll take it by const reference because we just want to sum up the values. We do not want to mess with those values, right? So const lets it be so that you like can't mess it up. All right, so now it won't even compile if I try to do this. Does that make sense? So that's nice. So I just want to go through that entire vector and sum it up. So for every int I in the vector, add it into res. And then res holds the answer. There. All right. So that's passing it by reference. I get space savings, and then I also have made it so that I can't mess up accidentally and like accidentally touch a piece of the vector v. I'm just using the reference for space savings. So when I call it on sum, I have 1,000 42s. I guess the answer should then be 42,000. And what do you know? We get that. Okay. So that's references. You're not allowed to forget them. All right, now let's talk about object-oriented programming, talking about making classes. So you're never allowed to forget this. It's a very, very important programming paradigm. So classes, remember, they're just, you make a type and you get to say what lives inside of that type. So every class, every object of your class has member variables inside of it and member functions that act on it. And like you're allowed to make objects, as many objects of that class as you'd like. And they all know how to respond to your messages. You can talk to them by sending them messages, and that's you calling methods on them. So it's like you're asking it to tell you, like you're asking a vector to tell it its size, tell you what's at index 42, stuff like that. It's like you're talking to it, and that's helpful for humans. We're just like imagining that our programs are in real life, and like we can ask our objects things, and they'll respond to us. They're sentient. So that's why everybody loves it, and so let's have some examples of that. All right, so here, the first one we'll do is let's do a stopwatch program. Let's use the ctime library. That one will let us, where's ctime? It has a clock function that lets us call it a bunch of times, and it gives us back a clock t, which is like the current time inside the computer, how many seconds have elapsed since we last called clock. So we'll just call it twice and like subtract. Okay, and then this clock type is like the number of like clocks that the number of ticks that the virtual clock inside the computer has run since we like last called it. And so we're gonna have to divide by a constant in the library, clocks per sec, to get back to like convert the clock ticks to the seconds. All right, so yeah, you read this and it will make more sense. But that's what I want. I want to make a stopwatch object. So I need a stopwatch class. All right, so I need ctime. And so like here's what I want to be able to do. I want to make a stopwatch, take it out of its box, initialize it, and then start the stopwatch. start it, and then be able to see how much time has elapsed since I started it. All right, it's like, I don't know, it's like while true, like just keep looking at the stopwatch. See out s dot get time elapsed, something like that. Does that make sense? So that's what I want to be able to do. It's very simple, but a good example of classes. So class stopwatch. Every stopwatch object needs to save when it started, right? We're going to have to save that, and so that can go in a private member variable. So we're going to call clock, the secret clock function, to get back a clock t, and that better be what we save, right? That'll be our starting time. So clock t starting time, all right? And that's what our start method is going to deal with. So let's implement that. It's like it's stopwatches start method, and so what should happen in the start method, we should just set the starting time member variable to a call to clock. Like go look at the clock inside the computer, give me back what it says. Save that so that we can use that later when we call it again and subtract. All right, so there's that one. And then get time elapsed. I want it to return how many seconds have passed. Get time elapsed. We'll have that return how many seconds have elapsed since we called start. And we're just going to use the starting time variable, and we're going to call clock again inside the method. So this can be const. This does not have to touch any of our member variables. Like starting time is already fixed. We already started the stopwatch. In theory, if we're doing this right. So it's stopwatches get time elapsed method, and what we want to do is look at the clock right now. So instead of starting time equals clock, we'll call it current time equals a call to clock, and that's going to be saved in a clock t type. It's like an integer. And yeah, now what we want to do, we'll return the number of seconds that have elapsed since between the current time and the starting time. So what we can do is subtract the two. So like current time is later minus starting time. That's how many clocks have elapsed since we started, and we have to now convert clocks to actual seconds. And there's this nice clocks per sec constant in the library that we can divide by. So we'll take that and we will divide it by clocks per sec. There it is. And unfortunately, both of these sides, like clock t's are integers and clocks per sec is an integer, so we're going to get integer division. We want nice, accurate decimal seconds, so we're going to have to make one side of this a double. So I'll static cast this first side to a double. It's already in parentheses anyway, that's perfect. So now the first side of the division is a double, and it will work out. All right, so I guess that's it. There's your stopwatch class, and we've got the implementation going, and there I am running it just until the end of time. Whee! And so look at it count up. It's counting slower than in real life. So like 1, 2, 3, 4, 5. It's slower than actual like seconds are inside of a computer. That's because it's giving back, this clocks thing is giving back how many seconds my program has been running. My entire program has been running, and this program is sharing time with like Vim on the computer, PowerPoint, all that other stuff. So it's not just this program that's running, and so the clock's a little slow, but it's how many seconds the program itself has had time on the CPU. All right, that's why you see it that way. But yeah, there it is. It's working. Cool. The next thing I want to show you is just a fun escape character that you maybe have never seen. I'll move this guy up here. That's fine. There's a \r character. Do you know what that does? You remember reading about it? Think about it. Think hard. It's short for carriage return, and it does something cool. If you haven't tried it, I'm about to show it to you. What it does is it performs a carriage return, and that is in terms of like the terminal acting like a typewriter. All right, so every terminal pretends that it's secretly an electric typewriter, and so what is a carriage and how do you return it? I have to draw a typewriter now. All right, hopefully you all know what a typewriter looks like. It's just it's a big box with keys. It's got a keyboard, right? And so there's that, and then you put your page right here. There it is. It hooks in, and then it has a little that is not an arrow. It has a little tool that whacks, like there's a bunch of keys and they're all like attached to a lever, and every time you press a key on the keyboard, it whacks the lever associated with that character onto the page, and then there's like a little band of ink that it passes through as it does that. So like it's really cool. Look into typewriters, I like them. But this piece right here, this is called the carriage, and it moves over because like when you type once, it whacks the page, and now the page needs to move that way so that you're typing more characters, right? And it's all in a line. It's like the page moves that way as you type, and eventually get to the end, and the bell dings on a typewriter. So then you press this, you move this lever, you move the lever back over, and it's going to like advance the carriage back to where it needs to go, right? You move it that way, and like now it's on the correct side of the page, if that makes sense. So yeah, as the type is moving that way, eventually you get to the end and it moves that way. Okay, so this is called the carriage, and yeah, to make it return it, you move it back to the left. All right, so that's what's happening, and every terminal is pretending to be an electronic typewriter called a teletype, and so we can command it to move its virtual carriage back to the start of the line. All right, that's my long-winded explanation. So because of that, because of all those facts, a bunch of backwards compatibility, if instead of I say endel here, if I say \r to move back to the start of the line, watch what happens. The terminal is going to pretend that it can do that. Now it starts overwriting on the same line. Isn't that cool? So if you haven't seen that or tried it, now you know. And it's going to be Control-C to stop all this. But isn't that cool? That's very useful, I think. Useful knowledge. All right, so that's my first example of classes. Not too bad, right? Got some member variables, got some methods, a const method. Let's get fancier now. Let's make a calculator class. So you can make as many calculator objects that function like calculators, and we're going to have a method per button on the calculators. This will be fun. All right. So think about it. Let's say that you want to, like, you take out a real physical calculator, and you want to do like 42 plus 55 and other stuff too. What does that mean on your calculator? That means you press the 4 button, you press the 2 button, you press the plus button, you press 5 twice, and then you hit enter, right? We're going to model all of that, all right, in a class. We're going to have a press the 4 button method call, a press the 2 button method call, and that's going to build up 42. Does that make sense? That's what I want. A calculator with buttons, and we have a method per button. That's what has to happen inside of a real calculator. We might as well learn how it's programmed. So yeah, for every operation, we're going to have a method. Press plus, press times, press divide. For every digit, we're going to have a method. Press 1, press 2, press 3. Though it will make it easier on ourselves to just like make a press digit method, like call it with 1, call it with 2 to press a single digit, all right? But we're going to have to use a bunch of digit press calls to build up a number, like press 4, press 2. Somehow we have to build up the number 42. See that? And then we'll have like a press enter button to actually do the computation that's been built up so far. Does that make sense? That's what we're going to do. All right, so we have to think about, like, all right, we're making a calculator object. What does it need to hold, like, by the time we press enter to know that we're ready and to, like, know what we want to have done? So if you think about it, every time inside of a calculator, when you press enter, you've built up a computation in terms of like a first number, a second number, and an operation. These are called operands, right? 2 operands and an operation. That's what's going on. Like by the time you press enter, you built up 2 operands and an operation between them. So we better store inside of every calculator object operand 1, the left side, operand 2, and then the operation. That's the data you need in order to like actually do the thing when the user presses enter. Does that make sense? That's what we need. So, all right, let's figure that out, and then like think about how you're going to build up a large number while I'm getting started with that, because that's going to be a little interesting, right? So here, I don't know, let's pretend I have it, and like I'll show it to you. Like this is what I want, right? Calculator C. I'm gonna be able to say like C.press digit 1, like 123 plus, or let's even do times, right? Times 456. Something like that. Does that make sense? Like that would work. Or actually, let's do the original. Let's do the 42 plus 55. I think that's useful. We can do these later in a test. So let's do 42 plus 55 exactly, and then like what we want is to be able to press enter, right? Like cout c dot press enter, and that will like do the operation and give it all back. Does that make sense? That's what I want, so that's what I need to have. So class calculator, it's got public stuff, it's got private stuff, and we've determined that we need at the very least 3 things inside of the calculator. Two operands, the stuff that it's working on, and then the operation, like the plus, the minus, the times, like what is it saving to remember to do later when we press enter. So let's just do integer math. So int operand 1 and 2, and then to save the operation as plus, minus, or times, we have options. We can like encode that as a number. We could use a string, like the word plus, the word minus. But I think the most efficient way would just be to save a single character. We'll save the plus symbol as the operation, the minus symbol, stuff like that. All right, that'll work. And then we have, oh, we got press digit, press enter, press plus, all those things. So here. So press digit, those are void, right? Void press digit, and it's like which digit are we pressing? And then, what else? We've got press plus, minus, times, and divide. We got those, and then press enter, better give the answer back, right? Do the actual results, not void anymore. Perform the computation. There. And yeah, if you think about it, we have to like build up numbers as we're starting all this stuff. All right, I hope that makes sense. So, okay, how do we build up 42? How do we build up 55? We're like pressing digits. And like, how do we know, like when we're typing numbers the first time, we're filling operand 1, and then the second, after we press the plus, now when we type digits, we're filling up operand 2. Do you see it's a little complicated? We better figure that out. So if you stare at the problem long enough, the answer is going to be a state machine. The calculator is a state machine secretly, isn't it? And then also, like, to build up the actual numbers, let's talk about that first. So like you're pressing, like you want to build up the number 123. You're going to press the 1, you're going to press the 2, you're going to press the 3, all separately. And somehow, like, the calculator doesn't know when you're done. So like the very first time you press the digit, it better save 1, right? Because maybe that's the number you wanted. But then when you type the 2, it better add a 2 at the end. Now it's 12. Then when you type the 3, it's like, oh, okay, I'll put a 3 at the end of that. But it never knows when you're done. Like, you could have stopped before the 3, and like it needed 12 to be saved. Does that make sense? So you need to build up numbers one by one, digit by digit. Does that make sense? And this is all going in like the operand 1 variable, for example, if you're typing the first number. So if you think about this long enough, there is a way, like how do you take 1 and add a 2? Like how do you take 12 and add a 3? Do you see kind of the math that needs to be involved there? If you think about it, how to add another digit to the end of a number, well, you need to first turn 1 into 10, right? Shift over that digit by multiplying by 10, right? Then it's 10, then you can add your 2 that you just pressed, plus 2. Do you see how that game works the whole time? Like now you 12 and you type the 3, that's again shifted over, right, to make 120, multiply by 10 again, and now you're ready to add in that new digit, the 3. Do you see that? Times 10 now plus 3. Do you see it? That's the secret. And so this will even work with the 1 if you start at 0. Times 10 plus 1, that'll work for the first digit. So that's a good value to initialize our operand 1 to. Initialize it to 1. Then when you type the 1 digit, multiply by 10 to make 0 again, plus 1. Now you got 1. You type the 2, right? Press 2. Now you multiply by 10 to make 10. Add 2 to make 12. So now it turns in from 1 to 12. And then finally you press the 3. You've got 12 in operand 1. You multiply by 10 to make 120. You add the 3 in to get 123. Does that make sense? So that's very necessary. All right. So you're building them up one by one. And then the other piece of the puzzle is like, all right, after you press plus, now you're working on the second thing, operand 2, not operand 1 anymore. So it's a state machine that will do that for you. All right. So when you turn the calculator on, you're in like, I'm typing the first number state, right? That's how calculators work. As long as you're typing digits, you're building up the first number, right? Press 0, press 1, press 2, all the way to 9, right? You're building up the first number, but the second you type your operation, then it better go into I want the second number mode. You see that? When you're typing more digits, they better fill up the second number. So the second you type any operation, plus, minus, times, divide, then the calculator needs to go into the second number state. That's supposed to be a plus. Second number. Does that make sense? And then, now you can build up, as long as you're typing digits, you're building up to operand 2, the second number. Okay? And then by the time you press enter, like you want the answer, that will reset everything, right? And go back to, press enter, equals. That will reset everything and go back to, all right, now we're ready to do another operation, so I need the first number again. Does that make sense? It's just a loop, but it's a state machine that gets you there. That's how you know, like I'm filling in the first number, I'm filling in the second number, operand 1 versus operand 2. Those are your valid moves inside of a calculator. Everything else is an error. So you could check for that. So that tells us that we need to program a state machine as well. Okay? So when the calculator turns on, so we better have a constructor, right? When the calculator turns on, we better zero out the operands. You can leave the operation garbage, that's fine. But then we also need a state variable. And I'll use a string to represent that. We need a string that represents what state we're currently in the calculator, because that's going to tell us like which, if we're in the first number state, we're filling in operand 1. If we're in the second number state, we're filling in operand 2. We only need 2 states though. Does that make sense? So that's what we need. Those are all the pieces now. It's complicated. A calculator is complicated, but now you know what's going on under the hood. So let's get all these ready. Oops. Give them empty bodies. Oops. Oops, I definitely did that wrong. Undo. It worked for that one though. Alright, I think I got back to where I was. I tried to record a macro in Vim that will like help me do this quicker, and I forgot to press end macro. There we go. See how it's filling in with empty bodies now? Look into that. That might be in Vim Tutor, but there we go. I've got empty bodies for everything. The very first thing I need to do in a calculator is initialize all this stuff. When you turn your calculator on, you want to zero out the operands for this reason so that we can build up numbers correctly. You want to zero out your operands, and then also the state of the calculator is I want the first number. All right? So we'll use the initializer list for that. So the state starts out as first number. You can use any string you want to represent that. I'll use that. And then the operands are set to 0. All right, and then you can have an empty body. That's all you're doing. You're setting those things in your calculator, and now you're ready, right? Now you know which thing you're filling when you press a digit, too. Like, if you're in the first number state and you press a digit, you're filling in operand 1. If you're in the second number state, you're filling in operand 2. So now we can program press digit based on the state I'm in. If the state is first number, then that means I'm filling in, right? I'm filling in operand 1. Add this digit to operand 1. Otherwise, that means it must have been the second number state. We'll add it to operand 2. And so it's going to be, for this first one, operand 1 equals what it is, right? We shift it over, we multiply it by 10, and we add whatever digit just got pressed. Equals operand 1 times 10 plus the digit. All right, and the order of operations make that work out just fine. And so that's that one. And then same for the other one. It's just we're working on operand 2. That's pretty clean. I like that. So, all right, now we know. And then if you press plus or minus or times or divide, what does that mean? Well, you better save your operation, first of all, and then also you better move to the second number state. Does that make sense? That's what you need to do. So if you ever, somebody's pressing plus, then we better save in our operation member variable. We got that. What operation we're doing right now. So it's a plus. We'll save it as a character. And then also the state is now changed from first to second number, right? Because we're pressing it right there in between. So the state should now become second number. Does that make sense? And you could be fancier here. You could make sure, like, you know that you shouldn't be allowed to like press plus times or divide after you've given the second number. Does that make sense? Like that this state machine should not allow that. But right here, we're kind of just like gonna give up and maybe start replacing the second number again. So you could have an if statement here to make sure plus is being pressed only in the first number state. That's the only place that it should be happening. But I'm gonna be lazy, all right, just to get this done faster. But you could do a better job than me. So when any operation happens, you save the operation and move to the second number state. Oops. So here. Save which one, and now we're in the next state. And then that's it, right? When you press enter in the calculator, what must happen now is we're gonna do the operation. We've got operand 1, operand 2, and operation all set. Do the operation, get it ready to return, and then also we're wrapping back around. So change the state back to first number, zero out your operands again. Does that make sense? You have to like get ready for the next move. Don't keep 123 in operand 1, because when you type new numbers, like you're just adding to that now, and that's not right. So you better zero everything out. So two things in press enter. We need to perform the operation, and then also we need to reset the state of the calculator. Those two things, and then we can return the answer. So we're eventually going to return a result. We'll fill it in with the right answer. So step 1, do the actual operation. So the operation depends on our member variables, right? It's if it was a plus operation, then we're adding 1 and 2. If it was minus, we're subtracting 1 and 2. So it's depending on the operation. If the operation was the plus character, then we're adding operand 1 and operand 2. Yeah? Else if it was a minus, then we're subtracting operand 2 from operand 1, because, right, 1 came first. It's like, otherwise, maybe it's a multiplication, and then there's only one other way to get there, and that's the division, right? So I'll just have an else for that. So that's performing the operation, getting the answer into result. And then we also have to reset the calculator. So that means set the state back to first number, because we were in the second number state, in theory. Again, you could ensure with an if statement that you can only press enter when you're in the second number state, but I'm being lazy. You could do a better job than me. All right, set it back to first number, and then zero out everything. Operand 1 equals operand 2 equals 0. All right, then we're ready to give the answer back. But that should do it. That's my press enter method. I hope you see it. Cool. So that's what it means to be a calculator, I think. So you got all these operations. None of them are const, right? These are all messing with stuff. And then here are your member variables. Your constructor zeroes out everything, sets the state properly, digit pressing, figures out which operand to mess with. And yeah, it seems to be the right idea. Do study this code. I'll give it all to you as usual. But let's compile and run. Boop, 97. All right, cool. That I think is right? 42 plus 55, yeah. That is 97. Cool. So it is doing the right thing. And what better way to make sure of that than to test it? All right, so let's steal and assert true and turn these into tests rather than just printing stuff. So I guess the closest assert true to me is lecture 27 TDD example. I think I've already got the string library up in here, so that's perfect. Let's put it just right here. And I'll make some tests now. So let's turn this one, for example, let's turn this into a test. I'll call it test calculator 1. Calculator 1. So instead of pressing enter and printing, let's assert that the answer was, what, 97? Let's do that. So instead of pressing enter and counting it, let's assert true that when we press enter right now, that the answer is what we expect. So let me clean this up. So if you press enter right now, the answer should be 97. That's supposed to be doing 42 plus 55. You see that test? So that should work, and we want to call that from main. Test calculator 1. And there we go. Let's see if that passes. It should, right? In theory. Awesome. And so yeah, let's make a couple more little tests here. Let's have a test calculator 2. So I'll steal a lot of this. So let's make a calculator, and let's check all the digits, right? Let's do some other operations, like 123 times, what was the one I was doing before? 456, yeah? That's pressing some stuff. And then the answer should be, honestly, I don't know, but we can let C++ deal with it. Like, whatever 123 times 456 is. Does that make sense? Like, that's my answer. There. Isn't that cool? I hope that makes sense. Like, that's an easy way, it's an easy way to fix that. And like, all right, the answer is like whatever that should be. Awesome. So there's another test. That's test calculator 2. And we should also test the fact that when you press enter, it should reset the calculator so you can do more stuff on the same calculator C object. So let's do some more operations. Let's do, oops, 78. What's another operation? Let's do minus. Minus 90. Then we've tried every digit at that point, right? You maybe also want to change press digit to not be allowed to like press digit 10 or something, because it would technically do that right now. We don't want that. So press digit 0, only a single digit. And what should happen now is like the calculator should have been reset, and when we press enter, it should hold the result of 78 minus 90. Shouldn't have any stray numbers in there. Should be doing that right. And it is. Awesome. So I hope this was fun. That's like what calculators really are doing deep down in memory. One day you may need to program one. Now you know. Now you're remembering how to test things as well. So I think that's everything that I wanted to say for those things. Let's talk about pointers now. I have that in our cheat sheet, right? So pointer, remember, that's a box that represents some other place in memory. So like int x, that's one box in memory. It has an address. And then you can make a pointer, an int star, right? That would hold the address of another int. So int star p equals null. Every pointer has its own memory. It's another box in memory. And the null pointer is a special address that you don't have access to. You'll get a seg fault if you try. It's just the 0 address, a nice default value if you're not ready yet. And then you can give it, right? Give p the address of x with the address of operator. That will let it point, right? It'll hold the address 100, point to the x variable, and then you can use it, right? You can dereference your p to get to this box and mess with the values there. All right, so remember all these symbols, all right? Pointers, the ampersand in a type means reference, right? It's not pointer stuff. Ampersand outside of a type, that means give me the address of something. Or bitwise and, I'm sorry. That's disgusting, but yeah, star in a type makes a pointer to an int, and then star outside of a type dereferences. It dereferences your pointer, okay? So yeah, all the symbols. So yeah, here it is on the slide. Yeah, pointer is just another box in memory, but it's capable of holding the address of somebody, all right? Somebody else. So the star is in the type for pointers, use the ampersand for address of, and star in an expression to dereference. Okay, so here's just that example. Let's do like an int pointer. So int x equals 42, my favorite variable. And so in addition to like looking like this, it really in memory has an address. Let's pretend it's address 100. We can then come along, make another box, make a pointer to that int, right? Int star y holds the address of x. That'll make another box y holding the address of x, which is 100. And y is another box, which means it has its own address. And then, but what it is, it's holding the address of an int. It's pointing to x. And so you can get to this box, get to the 42, and mess with it even by doing star y. You can dereference that pointer. Follow it. Star y, and a new line, something like that. Okay, so let's do that first. So int x equals 42, and then int star y equals the address of x. And so now y points to x. It holds its address, and now we can get things. So here, let's talk about all this stuff. Let's do cout.x. We'll print the 42, of course. Cout just y by itself. What is y? It'll print the contents of the box y, which is the address of x. Does that make sense? So y holds the address of x. Just y by itself will print the address, right? But star y follows it and gives you back the 42, the thing at x. See it there? So it's 42, then here's the address of x. That's what y holds, and then dereferencing it, though, goes to that address, gets what's in that box, 42 again. So yeah, star y and x, those are aliases for each other, just kind of like references. References are secretly using pointers, all right? So you can have pointers to pointers, that's fine. You can be like, all right, you can make a z, right? A box z that holds the address 104 and points to y. It has its own space, like address 112 or something. A z would be a pointer to an int star, right? Because that's what y is. So every time you want to hold its address, like you want to hold the address of an int, you put it in an int star. If you want to hold the address of an int star, you put it in an int double star. Does that make sense? So see that? Int double star. Z equals the address of y. So now z points to y. Does that make sense? So it's going to hold the address of an int star. That's what z is capable of doing. And so now let's talk about z. If you print just z, it gives me the contents of that box, which is the address of y. If you just print z by itself, it prints the address of y. If you print star z, you follow it once, it goes to y, right? It gives you this, which is the address of x. That's what I'm holding in it. And so it's double star, 2 stars to follow both of those to get all the way back to x. So the first star gets you to y, the next star gets you to x, because y is pointing to x. Now, if that makes sense. So here's apparently the address of y, here's the address of x again, and then there's the contents of x. So hopefully you can kind of see how it's working. All right. So yeah, that's how it's happening. And yeah, let's do an example with like pointers to an object, because that's the thing as well. You want to go inside, get the members. So pointers to a class or a struct. Let's do like vectors as an example. So like you can make a pointer to a vector. That's totally fine. You have a vector in memory. It has a starting address. You can hold and get that starting address with the address of operator. You can store it into like a vector pointer, VP. Have it point to your vector v. So the type would be, right, vector int star. Okay. So let's do that. I'll make a nice little vector. Have it hold 1, 2, 3. Then I'll have a vector pointer. Vector int star VP equals the address of v. And then you can do stuff to the vector through VP if you wanted to. But you can't do it this way. You can't say vp.size if you want the size of that vector that it's pointing to, because vp is just a number, right? It's just the address. You need to actually get to the vector. So you need to follow the pointer. Follow it, get to v with the star. Right? So you can say star vp.size. For precedence reasons, you need to put that in parentheses. That'll actually get to the vector. Star vp.size. That'll work. Alternatively, everybody hated that. It's too much typing. So they came up with the arrow operator. And this is equivalent to that. All right? So this line is equivalent to the above. And so they'll both give you the size 3 of the vector. All right? So you got to follow that pointer somehow and get to the operation or the member variable you're trying to work with. Okay? That's pointers. And yeah, just remember, this is all coming down to how memory looks, right? Think about memory as a big table, and everything has an address. Really, it's a starting address that's important. So, yeah, memory, what does memory look like? It's a big table that maps, just like a big long array, that maps addresses to values. Address 0 we don't have access to in user-level programs. The operating system can do that, but we can't. So 0 we set aside for our null pointer, and nobody gets to use it. But anything after that, you can values starting at address 1 and onwards. Remember that some values are big. They're bigger than just a single byte, because every address stores a byte value. They're just byte values. If you have like an int, for example, you make an int called I and have it hold a value, like 42. So let me draw that better. And say its starting address is 1, it's really 4 bytes long. So it's taking up addresses 1, 2, 3, and 4 if you're saying that it starts at address 1. And so you're storing 42 there. Okay? So yeah, multi-byte things, you always think about them in terms of where they start. What is their starting address? And then you know, just because it's an int, it's 4 bytes long, it's taking up. If it's starting at address 1, it's taking up addresses 1 through 4 then. All right? I hope that makes sense. What next? What next? Let's talk about the heap, a magical place. Do I have anything about that here? Not really. It's part of pointers, though. The heap, remember, it's a beautiful place where you can create dynamically allocated things. You can make memory that lasts as long as you want it to, and you get rid of it when you're done. All right, so that's lovely. How you use it is you say new and delete. So new and a type makes a brand new thing of that type on the heap, gives you back a pointer to it. And then delete, or delete bracket bracket if you made an array, takes a pointer to something on the heap and deletes it once you're ready, once you're done with it, okay? So here's like some code to deal with that. Int star I equals new int. So the way you say that, you think of it starting at the right first. You say new int, that creates a brand new int on the heap. And we can set it to something, it'll be like star I equals 42. All right, so let me draw what's happening here. So there's the stack and the heap. Stack. Anything with a name lives on a stack, or it's a global variable. And then heap is the new thing. So when you say new int, what that does is it makes a brand new box in memory on the heap, so it lasts as long as you want it to. And like it has an address, like 100 or something. It's shiny and new. Filled with garbage initially, just like anything else. Whee! Shiny new. And we can come along and put it somewhere. Put this address 100, that's what it's giving you back. Put that into I. So that's living on the stack. I holds address 100, and that's your window into the heap. You have to use addresses and pointers to get there. Then you can like dereference and set this to 42. All right, so that's what that works like. And then you can pass that around, just keep that address, so you have a window into the heap, have that box. And eventually, once you're done with it, you can say delete. Delete, and you give the address. So just I by itself. Give the address, so that's 100 of the place on the heap to delete, and it will go and get rid of it for you. Okay, so that's how that works. Let's see, might as well show that to you. The power comes from using this across function calls. You can pass it around, just like global stuff. So int star I equals new int. So now I points to a new int on the heap. And you can mess with it just like any other int pointer, like go dereference it, set it, look at the value, and then once you're done you say delete. Delete I. I'll get rid of it. Okay? So there it is, my 42. That's kind of useless. The whole point of using heap stuff is usually for dynamic arrays, and then also like you're passing stuff around between functions, and eventually you want to clean up after yourself. If you're just making an int here, you might as well just have made it on the stack. If you're only needing it in one function at least. So there's that one, just a simple example. That was storing a single integer on the heap. Also remember memory leaking. Do not leak memory. You need a pointer to something on the heap to access it, right? So if you lose this address 100, you like get this out of the stack for some reason. If you lose your last pointer to something on the heap, you've lost it forever. There's no way to guess what address was heap stuff. So here's a silly example of what could go wrong. So let's say you've done all this code already. Let's put it between here and the delete. Let's say you've set this memory up somehow. You've got this heap. So let's say you've got this memory. Here's I, it's pointing to the heap, and it holds 42. And then you come along and you say, accidentally, before deleting I, you say I equals new int. If you say that, when the memory looks like this, what it will do is it will make a brand new box in memory, set to garbage, and it will set I to hold the address of that now, so it chops off that pointer and points here. Do you see that? we've lost this thing. We have no way of knowing its address. We've forgotten its address. So that box right there, that int has been leaked. If you do that too much inside of a long-running program, the operating system is going to kill that program for you because it's going to run out of memory. All right? We don't want that. So remember to clean up after yourself. Delete it before you say something like this to get rid of that box, because you're about to lose it forever otherwise. Okay? So yeah, here's a good example of using the heap. You can make a vector, you know this, by like pushing back to it, but you can do that slightly more efficiently by using arrays on the heap. You can just immediately make an array of the size that you needed, and that is more efficient than making a vector and pushing back a bunch of times, because secretly the vector has to keep resizing itself. That takes time. So if you want the most efficient way to do this, here's a program that uses an array on the heap. All right, so it's a good example. So let's have the user enter a number, and then we're going to make an array of exactly that many things on the heap, so very efficient. And then we'll ask the user for how many things they want in that array. They'll start filling it in for us. We'll give them the chance to fill in the array with all the values they wanted, and then we'll calculate the median value in that array. Won't that be fun? So like the user is going to give us the median value in the array. So like for example, if they give us the array, I'm going to run out of room here, 1, 2, 3, 4, 5. What's the median of that? It's the middle thing, right? It's the thing in address 0, 1, 2, 3, 4, or not address, but index 2 for this case. What happens though if we got this array? Remember how to calculate the median of things? What if you have an even number of things? This is address, or not address, but index. What is the median of this? There's nothing in the middle. There's like 2 things in the middle. Remember that you have to take the average of the 2 middle things. That's how you calculate the median. So there might be 2 medians that you have to like average. And then also, the user can give us this thing out of order, can't they? So maybe they gave us the array 2, 1, 4, 3, 5. What's the median? It's still 3, right? That's nowhere near the middle anymore. So we have to sort our array first after we get the values, so that it is pretty like this, and we can calculate the right indices to go to in the middle. Does that make sense? Like that's my last example for us for the day. So let's do that. Let's ask the user for how many things they want to put. What's the array size, and they want to find the median of. So enter the size of the array. So we've got it, and let's make an array of that many things on the heap. Equals new int, and then you put between brackets the size. All right, and then when you want to delete it, you have to say delete bracket bracket that array. All right, so in between, we're going to do work on our array now. So we got to fill it in for sure. So go to every index, and then get it in there. So yeah, enter the next element. Int next element. Honestly, you could just do like cn into r of I. That would work, but I just want to separate these thoughts. And then r of I equals next element. So there it is. It's being filled. So we've got our filled array, and now we want to find the median. The median, even though this is an array of ints, might be 2.5. So it needs to be a double, first of all, in which we store the median. So median must be a double. That's interesting. And then to find the median in an array, we want to go to the middle value of it after it's been sorted, though. We don't want jumbled things because then it's out of order. We don't know where the middle is anymore. So we want to sort the array first. And so that's an algorithm. You remember how to call sort? It's on an array. It's sort, the name of the array, so the starting address, and then 1 past the end of the array address. So r plus size. Beautiful. So now it's sorted, and now we can do this right. Okay, so if the size of the array is odd, we want to calculate the middle by, it's kind of like size over 2, right? Size over 2, integer division will give me the 2. 2.5 gets chopped off to 2. That's perfect. If the size is odd, I can just do divide by 2 on the size to get the address, or not the address. I keep saying that because we just did pointer stuff, and we're still doing pointer stuff. I want to get the index. That's the middle index. So if it's odd, if the size is odd, if size mod 2 is equal to 1, there's something left over. It means it's odd. So odd size, the middle index is size over 2. That's perfect. And so the mid index is size over 2, and I want to calculate the median as that middle thing. So it's R of that mid index. All right, that's perfect. Otherwise, that means it's even size. All right. So you got two middle indices now. So say the size was 4. 4 over 2 is 2. That'll give you the right middle index. And then you just subtract 1 to get the left middle index. Does that make sense? So even size. The middle indices are size over 2 gives you the right middle. It's like, that's the 2 here. But you also want the 1. So it's going to be size over 2 and size over 2 minus 1. Does that make sense? So, okay. So int mid right, the right middle is size over 2, and the left middle index is size over 2 minus 1. And order of operations will work out for us there. And then, yeah, what the median is now, it's the average of those two. It's the average of those two using double division, right? Don't do integer division. The median is the array at that left middle plus the array at that right middle averaged together, so divided by 2. But don't do divided by just 2 because that's integer division. It's by 2.0. That'll make it do it right. And then, yeah, I've got the answer right in my median variable. That's the answer. But I do want to delete the array the second I'm done with that array. When I don't need it anymore. I've already got the answer in median by then, so it's actually right here where I can delete. Right? I need the array right up to here. I've calculated the median based on the array, of course. Still need the array still. And then now I'm done with it. So after we calculate the median, we are done with that array R. Okay, and it will be happy. So I think that's everything. Now we've got, at the start, we're making the array of a certain size. Say it's size 5, and let me enter in the jumbled thing, 2, 1, 4, 3, 5. So it's out of order. Doesn't matter because it will sort it and find that the middle yes is 3 of the sorted thing. Calculate the right address. That's perfect. So that's doing the right thing. Deleting the array at the right time and everything. If you gave it an even array, size 4, 1, 2, 3, 4, or in any order, it will correctly find that the midpoint or the median is the average of the two middle things. So you got your 2.5 there. All right. So it is working. Beautiful. Here's where the hard work happens. And I think that's it. That's all that I wanted to show you. So the heap, of course, you need pointers because the only way to talk about heap things is through addresses. That's what you get back after using new. And every new should have a corresponding delete or delete bracket bracket if it was an array that you made. All right. So that is a good start to our final review. That's where I want to stop. We will come back to talk about newer things next time.